and welcome. Justin here. Sorry for the studio. It's in a little bit of a state of moving, but I'm here and I'm live and I'm with Simon and Susan in the background. And just want to welcome you to the second installment of Redis data structures. Today we're going to be covering counting things at scale. Now that doesn't just mean using the data structures that I covered in the previous video. We're also going to use some of the Redis Stack modules, which includes Bloom Filter, Top K, and Count Min Sketch. So Simon is going to walk you through some of the familiar data structures that we've also gone through, but he's also going to show you some of the probabilistic data structures, I said it right, that we offer through the Redis module, Redis Bloom, and that's all part of the Redis Stack package. So I will be in the background answering any technical questions you may have to the best of my ability. And then I'll say hello to you near the end with some administrivia. If you want to check out that previous video, it is going to be on our YouTube channel. It's just simply called Data Structures in Redis. It's going to be our most recent video. And yeah, glad to have you here. Feel free again to ask any questions in the chat on YouTube or on Twitch, and we'll be able to answer those to the best of our ability. Hi, Simon.
Hey, Justin. How's things? It's extremely hot here today in England, so we're also having a hot day, and we're going to try some different content, but also different ways of delivering it. So hopefully this will go well. This is the first time, so bear with us.
Fantastic. Yeah, it's pretty temperate over here right now. I can hear my chickens in the background, so I know the chickens are happy. So if the chickens are happy, I'm happy. It's time for a great video.
Yeah, I can mostly hear laptop fan and stuff like that. But yeah, just before we got going, I just wanted to cover a couple of things that are kind of going on in the world of all things Redis at the minute. As always, we've got our Discord, which somebody earlier today was actually asking me a question about Top K, which is one of the things that we're going to look at today on the Discord. And I was able to answer them with a video that our colleague Steve did previously as part of our December event. And also with come and watch this when we do this afternoon, but also the bit of code that I've got for this afternoon. And then the other thing was, as part of this, we've been building up a community in Discord and other places, and we're on the lookout for members of those community to kind of like take the next step to become what we're calling a Redis Insider, which is our sort of champions program. So it's a way of getting recognized for your sort of interest and skills with Redis. And it's a program whereby you can apply for this, and we will support you to produce content and maybe go and speak at things, and basically become a Redis champion, so you can sort of elevate your profile in the community. And that's something that you can sign up for online, and Suze will share the link for that. There we go. So you can sign up for that right there. Okay, and I think we don't really have any more announcements or administrivia today. So what I'm going to do then is I'm going to do some content about counting things, which, how hard can that be? We all know how to count things, but it turns out there's many ways to count things. And sometimes being right all the time isn't actually what you need for a certain data set. So we'll explore some of those. This is mostly conceptual, and I'm going to use Redis Insight as well, which is the graphical tool for Redis. You can download that for free from our website. And I'm going to use Redis Stack. So we'll briefly cover what that is. And then I have a small amount of code in Node.js, but as with most things with Redis, you don't have to solve the problem in a given language. There's clients or drivers for pretty much every language that you can think of. So I happen to choose Node.js for this project, something both myself and Justin are familiar with.
And before I jump off, sorry, Simon, I just want to remind everybody that I'll be in the background while Simon presents, and I'll be able to answer your questions. So take it off, Simon.
Okay, thanks very much. So I'm going to go ahead and let's see, share the desktop to start with. So first thing we've got here is a web page. This is the home of Redis Stack on Redis.io, and we're going to use Redis Stack today. So first off, what is that and why do I need it for this, this demo that we're doing? So Redis Stack is basically open source Redis. So the Redis that everybody knows and loves with all of the features that it has, plus a load of modules that are pre-installed. So rather than having to come get them from us, compile them for your own operating system, install them and deal with them, or run different Docker containers, Redis Stack is a single bundling of Redis plus like 5 different modules that add different capabilities to Redis. So some of those might include JSON as a data type and full text search over that and over Redis hashes. And you'll see us talking about that a lot. Justin recently made a video about the time series capability in there. There's one for adding a graph database or modeling data in a graph database and using Cypher to get at it. And today we're going to look at something called Redis Bloom, which is a set of capabilities that adds probabilistic data structures to Redis. And we'll cover what those are and why on the face of things they might seem like a bad idea, but actually they're kind of the only way of doing some things as well. So we said that this was going to be a stream about counting things. So there's many ways we can count things. At the end of the day, there's 2 sorts of counting, really. There's like, I just want to count the number of times, say, a button has been pressed or something like that. Or I want to count the distinct number of like people that have passed through my turnstile or people that have voted in this election or vehicle license plates that have passed my camera. So we have 2 sorts of counting, and there's also 2 ways of doing this. There's like deterministic methods. So basically we're going to be right. And you think that would be a good thing all the time. And there's probabilistic methods where we're going to be taking an estimate and we'll be using a family of data structures that are generally known as sketches. And the reason why they're called that is because if you think of drawing something, you might draw a complete architectural blueprint for a building, and that's great. And it might take a long time and it might take up a lot of resource to do that. Or you might draw a quick sketch just to get the idea of it. And if you want that sort of approximation, or if you've got a data stream that never ever ends, like it's temperature sensors that are just constantly spitting out temperature, then you can't ever have an absolute right answer anyway. So the probabilistic data structures are interesting. They're sort of a family of things that make trade-offs between usually performance, accuracy, and storage overhead. And where this is interesting in Redis is to get that performance, Redis keeps a copy of all the data in RAM. So you kind of need to think about your storage overhead a little bit as well. So sometimes when we're counting things and we're doing this at very large scale, and especially when we want to count distinct things, we need to think about, is it really important to always be right all of the time, or is near enough good enough? And we get a sort of general flavor of what the trends in the data are. So moving on from just a web page, I've actually got Redis Stack installed and running. I use Docker to do that. So it's a single command just to pull a Docker container and run it with all of the modules. And we could sit here looking at CLI commands and typing those, but we have a interface called Redis Insight that we can see here. This is a graphical interface and it's free to download. And it comes with that Redis CLI in the bottom here that you might be familiar with already. So I can type in Redis commands, but it also has this view up here that I can see what's in the database. There's also a workbench view and some profiling stuff. And we can generally use this to see what's in a Redis database, work with it, and look at the overall health of the database. So my database is empty at the minute. There's no keys to display. There's nothing in here. So let's have a look at a really simple way of counting things to start with. So the simplest data structure in Redis is pretty much a string. It's what you'd expect. It's a binary safe string. And if you've used Redis as a cache, as a lot of people have, you'd be familiar with setting and getting strings and maybe using setex to set an expiry on those strings. They get deleted after a period of time. One of the things you can do with those is store numerical values in them. And one of the cool things with Redis is quite often there isn't a setup step. So if we just want to count something, we can start doing it. So here in Redis Insight, I can type a command. So I can do Inca, and I could say red cars, and I could say 1. And oops, I'm not connected to the server. Let's start again. red cars 1. No. Sorry, incr by red cars 1. So the incr command assumes that you're doing 1. But incr by red cars 1. We didn't have anything in the database before, and now we've got a value of 1 back. So that means that Redis has, we refresh this, stored 1 in this string here. So we didn't tell it that we wanted to initialize a count with 0 or that even we were going to use this for numbers. We just did an incr, off it went, and put it in there. So there's no initialization step, which, from a developer perspective, we're generally quite lazy people. That's good. We don't have to do set it to 0 or anything else. And if we want to keep seeing more cars, so we can do incr by red cars, we can do like more than 1. So we can do 3, and now we've got 4. And I can actually turn on the auto refresh here and turn it down a bit. And what we'll see is that's going to refresh the key space. When I do this, we now have 4 cars that we've seen. So in a single string, we've got 4 cars. And if we realize we've made a mistake, so we can do incr by red cars, I think we can do like -1. So really, the last one wasn't red. Maybe it was orange or something. We've now got 3. So very, very, very simply, we can count things like this. So we have an individual Redis key, we have numbers. There are incr by float commands that will work with floating point numbers as well. So we don't have to count whole things. We can count fractions of things, but we're going to assume we're counting whole things here today. So this is great, and it's a really basic way of counting things, and it works for us, and it's accurate. Sometimes we want to keep those things kind of joined together, or we want to associate a bunch of things together. So if we were counting cars, we could create a second key, and we could do like incr by blue cars, and say we've seen 4 blue cars for some reason. And now here we go, insights refreshed. We've got blue cars and red cars. And those are in separate Redis keys, and that's all fine, and we can maintain separate counters there. But what if we wanted to be a little bit more organized? So there's another data structure in Redis that does deterministic counting for us. And again, it's possibly one that you haven't used for this purpose before. So what I'm going to do is see if we can really quickly draw that for you. So over here, imagine we've got something like this big box here is our entire Redis server. And Redis is a key value data store. So it basically works a bit like this. So we've got key and a value. And we've got in here, we can have a bunch of keys and a bunch of values. So we could have like red and blue. And their values might be 3 and 4 and so on. But those are separate keys. And what if we wanted to sort of keep things organized and be able to get more than one type of car color out of Redis at a given time, for example, or get all of the car colors in one go? So for that, we might want to use a Redis hash, which is a mapping of field names to values inside a single Redis key. So that kind of looks like this. So we can do something like, let's change colors a bit so we can see a hash. So if we did something like we call the key name cars, and we created a Redis hash there, what that would actually look like would be you'd sort of have like a mini sort of Redis in here. And we would have keys and values. So now we could do red, blue, green, yellow, whatever we like. And then inside those values, we could store strings, but we can also store integers and increment them. So we could do sort of 3, 4, 7, and 9. So another way we can count things is we can have this single key here, cars, that essentially points to all of this stuff. So it points to a flat map of red, blue, green, and yellow. And then we can either get individual values, increment, decrement individual values, or just get all of them back at once if we want to. So let us go back to Insight here and see how that works. So there's a couple of ways I can do this. So I can create a key right here in Insight and get rid of the command line. So I could create a hash here and I could call it cars. And then I can enter some fields. So let's do red, and we'll start off with a value of like 3, and then do blue. And what do we say for blue? I think we said 4. Doesn't really matter, but we'll try and stick with the sketch. And green was 7, and yellow is like 9. So when I hit add on that, now I've got a new key that I've added within Insight itself in a graphical way. I didn't have to type any commands, I just filled them out. So here we can see I've got my values, and if I go back to the command line here, how do I now count something in this structure? So inside my hash, we've got all of these fields, and if I want to increment or decrement one, I can use the hinker by or hinker b or hinker b, as people on our team sometimes call it, command. So hash increment by, and then we have to give it a key. So we're saying cars, but cars itself is not a number. The fields inside there are, so we need to tell it which one we want. So let's go for blue, and let's say we've seen another 2 blue cars. Now we get 6 back out of there. And what's happened when I refresh this over here is you'll see that blue has gone to 6. So we have got 6 blue cars in our new hash. So we have a question here. Can we have nested hashes? The answer to that is yes and no. So inside a Redis hash here, it's a flat map of what you see over here on the diagram. So it looks like this. If we were to start a new diagram, then what we can do is here in Redis Stack, we can have, imagine we've got our sort of key value space going on here, and I could call it cars again or anything I wanted to. Redis Stack comes with a module called Redis JSON, and that basically allows us to put JSON inside here and work with it atomically. So we can write JSON paths into different parts of the document, and then yes, we can get numbers out of there and increment or decrement them, or just store arbitrary structure. So I could sort of have things like manufacturer. My writing is not going to be great on this iPad. And then we could have like Ford, and then 0, and then GM 12, and so on. So in that way, using Redis JSON, we can have nested, but hashes themselves don't nest. Hashes themselves look kind of like this structure here. Okay, so hashes on the face of it look like a really good way of counting things, and you can see one here. And they do accept a pretty arbitrarily large number of fields. So if we wanted to count lots and lots of different things in here, so what's the frequency of red, blue, green, yellow cars, then we can accommodate that in the hash. The data structure will cope with it. The big O of accessing it is constant, so we can have more fields in there. It won't be a problem. What would become a problem would be if we said to it, can we get all of the fields back out? Because that's like a big O of n operation. So the bigger that data structure gets, the longer it's going to take to pull those things out. However, it would have to get quite large for that to be a problem for Redis. So the other thing that's a concern here, but not at this scale, is, and we can see it here in Redis Insight, up here we have a size of what this key is occupying in Redis, so how big it is. And that's going to grow as we add more and more data to it. So in order to get precision here, so absolute precision being right all the time, we are going to need to have a data structure that grows all the time. And that's one of the things that we're going to have to live with if we want that. So we don't always want that. And one of the capabilities of Redis Stack, it has a module called Redis Bloom. And that comes with the data structure called account min sketch, which might be something that you've heard of before. And it might be something that's new to you. So I'll quickly just try and draw that out, and then we can actually look at how it works in code later, because we kind of need a lot of data to make it work. We have a quick question about, does Redis JSON use more memory compared to hashes for the same amount of data? Going to depend on your JSON, but yeah, probably will, but then you get a lot of more functionality for it. So trade-offs. Okay, so let's go and look at what does a count min sketch kind of look at to the extent that I'm able to draw one. So we'll have a new color here. So what we were doing before was basically storing values. So the actual value, the color of the car, or whatever the data item in the data stream is, and the count of it. So we had something that looked like, sort of red to green 12, etc. So we're storing both of these things, counters and the actual values. If I then clear this down a bit, what the problem with that at scale becomes, if we've got a data set that either never ends or is just extremely big, is we're going to start burning through memory, and we're going to have to make some trade-offs. And what the probabilistic data structures do is they sort of trade off between accuracy and usually storage space. And the way that they do that is generally by hashing, which might be something that you've sort of been familiar with in computer science generally. So roughly, if I took some sort of identifier, like, I don't know, let's say, have a white pattern so we can actually see it. If I took some sort of identifier like the word whale, and there's a reason for this, the data set I'm using later is all the words from Moby Dick. So if I took an identifier like whale and stored that somewhere, I've got to store that identifier along with the count of how many times I've seen it. What the probabilistic data structures do is they use hash functions to reduce that sort of storage that's going to grow consistently to some sort of like constant bit array mapping. So instead of storing the actual data, we're going to store something that is basically a bit array. And we are going to run this through some hashing functions. So we'll call those like hash1, hash2, and then hash n for however many we've got. And when we run whale through each of these, it's going to come out with a number that is a position in each of these bit arrays. So imagine this was like 0, 2, 3. And this in our sketch is the row for hash1, hash2, and hash n. Then we've got, we would say 0 here, 0, 1, 2 here, and 3 here. And then next time we see whale, it would hash to the same thing, and we would basically increment these counters so that there. And what's going to happen with hashing here is we're going to get collisions, and sometimes some of these are going to get updated when they're not supposed to be. So, or when it's not something from whale. So what we end up with is a situation where like one of these might read 3 and one of these might read 4. And basically the way that a count min sketch works is it has a configurable width of this bit array here, which is like your fixed item, and a configurable number of hash functions here. And then when you want to get an approximation of how many, what the count is for a given item, you run the hash functions, get the positions, and then take the minimum from all of those. So it's never going to undercount, but it might sometimes overcount because that minimum might still be wrong. So we'll look at what that looks like in code later. But this trade-off of accuracy and also losing the original data will save us quite a lot of memory. So this is not for you if you need to get the original data back, because by the time we've stored whale in here, we can't get it back out again and say, hey, give me all the things that are in this data structure. We can just say, give me the count for whale, and it will run it through the hash functions and see what maps to We can't get all of the words out anymore, which it's a trade-off. It's a pros and cons. So that is a couple of ways of counting things, one of which is probabilistic. And we'll look at that with some code later. But the other problem that I wanted to look at now is the one concerning the other sort of counting that I was talking about earlier, which is counting of distinct items. So let's take a look at that. So imagine I'm trying to work out like who has passed through a toll gate or something on a road. And yeah, we're storing cars by license plates, and maybe license plates look like it. Oops, that's a bit thick, isn't it? Let's make that less thick. And so maybe license plates. Oh, that's still a bit thick. Maybe license plates look like ABC 1, 2, 3. So it's three letters and 3 numbers. And then we've got another vehicle, DF 987, and then we've got RED 15, sorry, Redis. And then we've got ABD 1, 2, 4, and so on. One of the ways that we can determine how many different vehicles have passed through our toll gate today, or whether this particular vehicle has passed through our toll gate, is by putting these into a set data structure. So I've drawn a circle around these because when you talk about set theory in math, quite often you talk about Venn diagrams and you end up with those sorts of things. So imagine these are all in a set. A set in Redis is one of the built-in data types. So we can store this as a key. So we could call this license plates. We'll actually go ahead and do this in a minute as well. And then we can ask it questions like, how many, and it will say 4. And is ABC 1, 2, 3 in there? And it will say, yep, it is. And we can be absolutely certain of that. And then we can ask it things like, is DEF 999 in there? And it will say with absolute certainty, no, it isn't. So again, this looks like a really good data structure for this sort of counting distinct things. I've got the ability to put things in there. I've got the ability to ask it how many there are. And I've got the ability to say to it with absolute certainty, is this specific thing one of the things that you've counted already or seen or not? And it will always be right. So let's just go ahead and model that over here in Redis Insight. So I could create another key. And let's do it up here because kind of fun doing it this way. So let's do a set. And we'll call it license plates. And then license plates. And then a set has members. So we'll say AAA 1, 2, 3 is one of our license plates. And then AAB 993 is one of our license plates. And then BCD 21231. And we'll give it one more. So we'll give it 111. Okay, so add that key. There we go. So now we've got a, put an empty one in there. Let's get rid of that. So now we've got a set in Redis, and that has a cardinality or a length of 4. And it has this data in it. And the data's still in there. So this is deterministic data structure. We've saved this data in there, and we can now ask it questions. So I can use the CLI here. And all the Redis set commands begin with S. So I can say to it, S card. So what is the cardinality, or how many do you have of license plates? It's going to tell me 4, and we know that it absolutely has 4. I can then say to it, S is member, which is, have you got this license plate? And it's in the key license plates. And I could say AAA 1, 2, 3. Say 1, which is a truthy response. So yeah, we've seen AAA 1, 2, 3 before. If I then say to it, have you seen that kind of cool license plate RED 15? It'd say, no, I haven't. And we know with certainty that it's not seen it. If I then want to add that license plate, I can do sadd for set add, license plates RED 15. And I get 1 back that says the set's been modified, 1 new thing was added to it. So there it is. We now have 5. And if for some reason that card drives through the toll gate multiple times a day, imagine we have a policy that once you've been through, you've paid your toll for the day and you don't have to pay anymore. So let's have them drive through again. This time we get 0 on the set. It's not been modified. And that's because the set doesn't allow duplicates. So if we try and add one that's in there already, it's not going to allow that. So this is useful for that sort of distinct behavior. I can add this all day and it's just not going to let me. And it won't change the cardinality or the size of the set. So on the face of it, sets look really, really good for this. And there's 2 questions that they can answer for us, which is like, how many distinct things have you seen? And have you seen this specific thing? They can also tell us everything that they've ever seen. So we can do S members license plates and say, get me every license plate you've seen today, and there they are. That again gets a little bit dangerous time complexity wise as your set gets big, because that's a big O of N command. So the bigger your set gets, the longer this is going to take on the Redis server. So with certain sizes of data set, this ability to check, this ability to check if something is a member of the set is desirable, but at certain data sizes, you have to think about whether being right about it all the time is necessary. So again, there's a probabilistic data structure that can kind of take over from this aspect of the set as the data set gets really, really big. And it's going to trade off quite a lot of memory usage, because we're remembering all of these license plates, and that is going to get big with like millions of cars. It's going to trade that off for some accuracy. So basically, it's going to lie to us sometimes. And that data structure is called a Bloom filter. So let's have a go at drawing what a Bloom filter looks like as well. So if I get my pen back here, and hopefully we can draw this. So with a set, as we saw, we kept the data. With a Bloom filter, we're going to hash it again. And the way that the Bloom filter is going to save us a lot of memory is we're going to hash things into a byte array. So imagine I've got a byte array, and obviously we would have a lot more bytes than this in a real one. So this is just a trivially small one that fits on the screen. And I want to do 2 things with this Bloom filter. I want to store identifiers in it, or terms, or things from my data stream, or whatever they are, so my license plates in this case. And I want to see if the Bloom filter has seen them before. So in order to store them, we use a number of hash functions again. So imagine we have the license plate ABC123, and imagine I've got 3 hash functions, and the results of those hash functions are all moduloed or divided into numbers that fit in this bit array here. So ABC123 is going to generate, we'll run it through 3 hash functions, it's going to generate 3 positions. So imagine it ended up, say, there, there, and there. What we would do in that case is set these values in the Bloom filter to 1 rather than 0. And then we've stored our license plate in there. So if we store another one, so let's try DEF178, for example. That might hash to here, here, and let's say here. So what's happened here is we've got 1 bit that was already set. So that's kind of like a hash collision with another license plate, and 2 new ones that will set to 1 here. Again, obviously in a real one, you would have many more bits, and the collision is going to be less likely, but iPad-sized demonstration, this is what we're going to have. And then finally, let's add a 3rd one here. So imagine I've got RED15, and it hashes to like here. So we'll set a 1, and here, nothing already set, and here there's a 1. So we've put 3 things inside this Bloom filter, this data structure. The key thing to notice is the array of bits didn't get any bigger here. So we can keep putting things in and the array won't get any bigger. So we've got like constant storage and we've got constant insertion time because we're doing the same number of hash functions and just setting bits. But what will happen over time is this will fill up. So we need to scale that bit filter, bloom filter correctly and sort of ultimately handle the condition where it's filled up. And the good news is Redis is going to do that kind of for us. So we'll look at that in a bit. So now we put some things in there. How do we get them out? So if we go to a different color here and we want to get the license plate, say RED15, then we run it through the same hash functions and that position maps to a 1, that position maps to a 1, and that position maps to a 1. So if this was a set, I'd be drawing a great big green check mark here and saying, yep, we got it. We know it's in there. Because it's a bloom filter, I draw a question mark. So why am I drawing a question mark? That's because the way that hashing works is we get collisions. So other things might have hashed to those same bits, but something hashed to those, and Redis would have hashed to those if we'd have added it. And it turns out in this case, we did add it, but we don't know that because we've hashed away the data. So what we can say here is there's a high probability, and that probability is a function of number of hash functions and the size of your bloom filter. There's a high probability that Redis does exist in the bloom filter. So let's try another one here. We can use license plate. Let's use one DDK223. And let's say that that hashes to over here. So that's a 1. And then it hashes to here. And this one's not set. So what we can do actually now is just stop. We don't necessarily need to do that other hash because we found a bit that wasn't set. So DDK223 can't possibly be in the bloom filter because if it had been, that bit would have been set either by it or something that clashes with it. So we can say with absolute certainty, big red cross, no, that isn't in the bloom filter. And we can say that Redis maybe is. Then we have a third case here where if we went to check something else, so imagine we went to check like AKR232, and AKR232 maps to this one, and like this one, then all of those green lines here point to 1s. But you see the problem here is like AKR232 isn't in the set of things at the top because we never added it. But other things that we did add all map to the positions that AKR232 does. So this is like a false positive. So this will say, yeah, maybe, but in fact, we never added it. So that's the bloom filter in a nutshell. It's kind of one of the easier ones to draw, I think, and there's some really good visual tools out there on the web to look at them. When we use it with Redis, we will use it in a way that Redis will size and scale it for us, given some parameters. So we don't need to necessarily worry about how big things need to be. We just need to think about our data set a bit and a desired acceptable error rate. And we'll look at in some code how we manage to save a lot of memory with these. So the other sort of counting that I wanted to cover is a ranking type counting. So you might have heard Redis getting used for things like leaderboards quite a lot. And sometimes you also don't need to know necessarily like how many votes somebody's got that accurately, as long as you can tell who's in the lead. So you wouldn't run a presidential election on that basis, but you might run a vote on like a social media site for like who's the greatest pop star of the 21st century. You know, as long as we've got about the right number of votes, it doesn't really matter. And again, the difference between using a deterministic data structure and a probabilistic one is going to be the memory for a little bit of accuracy. So one of the ways that we can rank things in Redis is using something called a sorted set. So that's like a set in Redis. It keeps a group of members or identifiers, and it associates them with a score, and it doesn't allow duplicate members. So it also keeps them in order. So we can sort, well, we don't have to sort them. They're already sorted. We can ask it for them in sorted order and basically build some sort of leaderboard like that. So if I were to create a sorted set, let's do this one at the command line. So I'm going to clear that. The sorted set commands all begin with Z or Z in Redis. So I'm going to do Z add. Again, you'll notice there's no create step here. I'm just putting something into a sorted set and Redis is creating it for me. So what I'm going to do here is do Z add and we'll call it, I don't know, let's put something really imaginable, really imaginative like leaderboard. And then I need to provide it with some scores and members. So let's say we've got 10 points for Justin, who we spoke with earlier. And over here, I've now got a new key appear on Redis Insight, and I can click that, and you can see we've got a leaderboard here of Justin with 10 points. There's nobody else in it at the minute. So if I do Z-add leaderboard, and we do 11 points for Suze, and then I'll give myself like 9 points, and let's give 14 points to, say, Brian, and let's give 16 points to Savannah, and let's give 9 points to Guy. So I don't know how that looks, but let's refresh this and see. Now we have all of these people in our sorted set, and it's ordered them by score. And we can reverse that, so we can see probably what you want for a leaderboard, which is the highest score down to the lowest. It's kept all of this information, so we can ask it things like who's in the sorted set, and it will give us that back. We can say, there's a certain person in there. We can get their score back and all of that great stuff that you saw with sets. If we want to update somebody, then we basically just overwrite them and it will change their value, or we can use Z incur by. So I could give somebody some more points. So if I decide to give, for example, Justin the key name, leaderboard. So where is my sorted set? And then how many points I want to give. So 2, and I'm going to give those to Justin. Then great. And then if I refresh that, you'll see Justin is now just nicked above Suze. So we have a leaderboard here. When these get really, really big and you're counting lots of people's scores, you maybe just want to see like however many the top so-and-so are, or the top however many around me. So you might want to know like who's above and who's below me, or ask the leaderboard questions like that. Sorted set's great for that sort of thing. So we can ask it things like the range. So sorted set range, leaderboard, which is my key. And then I can give it a start and an end position, so like 0 and 2. And then I can tell it I want that reversed, so highest score first, and I want it with the scores back. And what you'll see is we get a fraction of that sorted set back. So I just get my top 3, so the people who are currently in the medal positions, if you like, from that command. So sorted sets are great for this sort of thing. And we could use them for counting lots of stuff and keeping, say, a ranking of like the top 10 words in a book or something. And again, it's going to be totally accurate, but at the expense of taking up memory. So as we add more and more things, the adding of those things is not a problem because the data structure scales like that from a performance perspective. The asking it what somebody's score is not a problem. But what the problem is going to be is we put more and more data in there. It's just going to need more and more RAM to, on the Redis server for that particular key. So there is an alternative way of looking at ranking things that's probabilistic, and that's called a top K, and that's also built into Redis Bloom. And we'll look at that one in code. But basically what that's going to do is approximate the ranking of things at the expense of getting the counts right, and also it's not always going to be right, but it's going to be pretty good enough and it's tunable. So with that said, we've kind of done a lot of theory and stuff here. So I'm going to jump to some code that actually puts something into all of these data structures at once, and we can see how that goes. So I'm going to don't do this in your production Redis, but I'm going to flush that database completely. So we've got an empty one now, and we will close that down and come back to this later. So what we've got here is some node code and a data source. So what we've got in our data source is a lot of words. So let's just make this bigger. Where did these words come from? They came from Project Gutenberg. So Project Gutenberg has the text of like classic and copyright expired books online. They came from there, and these are the words from Moby Dick, just as they are from start to end, with basically all of the little words removed. So what a search engine might call stop words. So anything that's shorter than 5 letters, I've removed, things like the, he, and so on. So we've got a lot of words here, and what we're going to do is have a look through a bunch of data structures and see how they compare when we try and get them to do their thing with these words. So here I've got some node code, which, as I said earlier, it could have been Python code, it could have been anything really. The takeaway, what it's going to do is we're going to have a key for each of these data structures. So we're going to have a set, a Bloom filter, a hyperloglog, which is not what I've mentioned so far, but a hyperloglog approximates the cardinality of a set. So we use a Bloom filter for that. Is this something we've seen before type question? And we would use a hyperloglog for how many of these distinct things have we seen before. And they're both space efficient and they approximate. So they basically don't store the original data set. We use a top K to see if we can figure out what the sort of top 10 ranking words are. We use a sorted set to do the same thing. So compare the probabilistic with the deterministic. And then we'll use a hash just to count things. So each word I'm going to give a field in a hash, because I said hashes can get quite big. And we're going to use that h-increby command to count those instances of words. And then we'll do the same thing with a count min sketch. So we don't need to really worry about how this code works. It just creates a client and connects to Redis. You do that in any programming language. In Node, you do it like this, and then you just await that connection. And I've just got some code that deletes keys out of the database so that we don't start counting on top of a previous run of this. And I've said so far that a lot of data structures in Redis don't need initialization. So when I put something in a set or a sorted set, you didn't see me initializing one or setting that string counter way back at the start to 0. We just kind of got on with what we were doing. With the probabilistic data structures, hyperloglog's kind of an exception in Redis. It's kind of got a fixed error rate, and it's built into Redis itself. The other ones, the Bloom filter, the top K, and the count min sketch, are all built into Redis Bloom, which is part of Redis Stack. And these are configurable, so they're sort of general purpose. So you can pick an error rate and the data size or whatever the tunable parameters for that data structure are. So if we look at the Bloom here, for example, I'm guessing roughly how many things I might want to store and giving it an error rate. And then it's going to figure out the size of that array that I need for the bit array. And it's going to manage all of that for me. I'm not going to be dealing with bits in Redis. I'm just going to be dealing with a higher level Bloom filter API. Similarly for the top K, I'm going to tell it, well, how many things do I care about ranking? I'm going to say 10. And then we've got some tunable metrics here for like how big its structure is, and also what the decay rate on that is, which is basically how it's going to forget about things as they fall out of the ranking. Then for the count min sketch, I can also configure a couple of things that is going to determine how many hash functions and how big that grid is. So we can tune these according to our problems and sort of play around with them with the data set, which is good. We've got flexibility here. Just means you need to spend a little time looking at it maybe. And then the majority of this code is basically just a big loop that goes through all of the words. And then for each word, we're just going to drop them in each data structure. So I'm going to put it in a hash. So the word's going to be a field name in a hash. I'm going to add it to a count min sketch. I'm going to add it to a set. I'm going to add it to a Bloom filter. Again, you'll see the Bloom filter and the set APIs are quite similar. So if you started off with a set and then you hit a memory problem and you wanted the same sort of solution, but you wanted to swap that probabilistic data structure in, save yourself some memory at the cost of a bit of accuracy, the code changes are pretty minimal. I'm going to put it into the hyperloglog with PF. The Redis commands for hyperloglog all begin PF because those were the initials of the mathematician that came up with the algorithm for it. And I'm going to do the same with the top K. And then for the sorted set, I'm going to use that Z or Z increment by command that we used before. So you'll see basically me putting it in there and saying I want to increment it by 1 in the couple of cases where we can configure what we're incrementing by. And then after that, we're going to pull some information out of Redis. This is a lot of console commands, but basically we're going to use the memory usage command, which is what you see Redis Insight using for estimating the size of a key. And we're going to have a go at figuring out how much memory the key for each data structure has in Redis. And then we're going to ask it some questions and see how the two sorts of data structure compare. So I will share this code. It's currently on a branch in a repo, but I will share it on the YouTube description for this and also in our Discord afterwards. So if I go here and run this, there's not going to be a lot to see here on the terminal for a minute or so while it goes away and does this into a Docker container in my poor Macintosh that's also screen sharing an iPad and doing all of this Twitch stuff. But what we can do is quickly pop over to Redis Insight, and it's already refreshed here. So you can see I've got some different keys. So I've got Moby Dick words, top K, sorted set, and so on. Some of these are viewable in Insight. So if I click on this, you'll see we've got each word and its current count. Can't really do a lot with it here in a hash. I can't sort these, but I can look at the sorted set where we've got members and scores. So currently 79, 76, those are sort of high scores as we go through the data set. The count, min, sketch, and the top K, we can't really see those in here. There isn't a view for those at this time. Similarly with the hyperloglog, that's just an algorithm. So it's a load of binary in there. You have to use the commands to visualize it. If I look in the set, we can see all of the distinct words that we've put in here. And we can see this set's taking up like 260K at the minute. We look in the Bloom filter, which is also tracking the distinct words. No, it's like 27K, so it's 10% of the data size. You know, at this size, that doesn't really matter. But if we had this huge data set, like never ended, or have millions of records a day, or whatever time period we're keen on, then this does make a big difference for potentially not too much difference in the accuracy of the output. So let's go back and see if no, we're still going. When I tried this before, it could take up to about 3 minutes to do this. So we'll let it do its thing. And I will also turn off QuickTime because I don't think I need to draw with the iPad anymore. And it is probably burning up some resources. So let's find QuickTime and quit it. Give this machine some resource back. Meantime, we can, of course, go over here. This is refreshing itself every now and then. So we can see that this is continuing to get bigger and bigger and bigger. This is also continuing to get bigger. The count, min, sketch is a fraction of the size of the hash. The hyperloglog that's counting the cardinality of this set, that's actually going to top out at 14K because that's pretty much as it needs to count a very, very, very big number. So it's not, I don't expect that to get any bigger. And the Bloom filter, again, is a fraction of the set. So the hyperloglog and the Bloom filter are kind of doing two jobs that the set does for us in one data structure. So the set does, have I seen you before and how many of you are there? Hyperloglog's handling that, how many of you are there? Set's handling, have I seen you before? And we are still going here. This may take longer than I expected, or longer than it has done before, because the machine is very busy. It may also not help, actually, that Redis Insight is kind of polling Redis here to ask it about all the keys. So I'll just drop that. I'll leave this in the corner, come back to the code for a minute. So yeah, all of these data structures have really, really simple APIs. So adding things or incrementing them is either an add or an inca type command. And then when we want to look at things, so for the count min sketch, we can say cms.query, give it the name of the key that's got count min sketch in it, and then the value that we want to get a count for. So porpoise here, for example, we get a count for. But of course, what we can't do, which we could have done with the hash, would be say, hey, get me all the values. So if we don't know that porpoise was in there, we'd have to like just go in there and guess. So we need to get a 0 back or we get something else. Whereas with the hash, we can see what's happening and see what's in there and know that these are the distinct words in the book, but we have burned up all of that memory. Similarly with the set, we've got all the distinct words, whereas with the hyperlog and the Bloom filter, they've gone away by this point. So we've got a sense of them, but we don't have the actual words. We can't reconstruct the book from that. Sometimes that's a good thing because sometimes you want, with license plates, maybe you just want to count license plates for traffic survey reasons, not for charging reasons. So you do want some sort of anonymized license plate thing. So my machine is burning up here. I would love to know. Oh, there we go. It's just finished. So let's see what it's done. So what we've done is we looked at some of these data structures and how much memory they used and how accurate they might be. And let's go back to that result. Now I've made it bigger. So the hash used just over 1 megabyte of memory. And we've asked it about some words. So it reckons whale was in there 907 times, porpoise 19, and Jonah 70. And that's probably correct. Well, it should be correct because it's deterministic. When we look at the count min sketch, it's used 109K. So it's used like a tenth of the memory. And it's, as you would expect, it's in the right ballpark, but it's not dead on. So it knows that there's about that many and it's not far off. And that's tunable. So in cases where we're okay with saving like 90% of the memory for that, then this is a good choice. We can also say how many fields are in the hash. So the hash has 16401 fields. We loaded everything into a Redis set. So how many words were there? The cardinality of the set, 16401. So again, the two probabilistic things agree that there was 16401. The set used nearly 1 megabyte of memory. And when we count how many distinct words are in the set using the hyperlog, which is probabilistic, it got 16362. So it's pretty close. It's a little bit under. But again, look at that memory savings. We've got 14K. So if you only care that there are like 16,000 or between 16 and 16,500, that level of error, then this is quite an interesting way of doing things. Saves you a lot of memory. And equally, the set used 973 kilobytes of memory and the Bloom filter used 27. So we can ask both the set and the Bloom filter, have you seen these words? And the set will always be right. The Bloom filter will mostly be right with configurable error rate, and it's saving a lot of memory. And obviously, the more you dial down, I want that error rate to be smaller, the more memory the Bloom's going to use, but it's still an order of magnitude cheaper memory-wise. Then finally, we looked at the top K and we basically asked that to keep a track of the top 10 recurring things in this stream of words. And it got these words. And it's optimized for ranking, not scoring. Whereas the sorted set is going to be absolutely accurate, but use, again, a lot more memory, 1.6 meg. It's like the biggest one of all of them. And the top K just used 33 kilobytes. And again, it's in the right ballpark. So we don't really care about the counts here, remember. We're just showing those for information. What we care about is what are the approximately top 10 recurring things in this stream of data we've got that may never end. And the top K and the sorted set mostly agree on that. So again, for the memory savings, it's quite compelling. So that was kind of all I've got for today, which hopefully wasn't an explosion of data structures and how the heck do we use these. Thanks for bearing with me with going through some of the drawings here. And the only other things to do, I think, are take a look at, if you're interested in all of this stuff, then head on over to Redis Stack and get yourself a copy of Redis Stack. It's got all of these things in it. You can install it with Brew if you're a Macintosh person. You can run it on Docker. You can click over here, try Redis Cloud, try a 30 meg instance of it with all of this functionality for free in our cloud. And if you get stuck and you'd like help, we have a Discord server at discord.gg/Redis. And there's channels for all sorts of things. So here we're looking at the Redis Bloom channel where we talk about probabilistic data structures. And people come here with like things they're doing with them, cool projects they're working on. And you can also ask for help if you don't understand something or you'd like our advice on how, what's maybe the best way of doing it. So with that said, I think it's time to stop sharing the desktop for today and bring Justin back in really quick. Hello.
Hello, hello. Great work.
So yeah, that was a lot of data structures and diagrams.
It was really great though, and you have a masterful command of the iPad. So thank you for bringing that illustration onto the show. That really helped.
Yeah, for those watching, that is just the built-in Notes app on the iPad, so you can get quite a lot done with just the stuff that comes with it. I was using the Apple Pencil, which I do find quite helpful because it's a lot lower or higher resolution than using your finger, so you can get more stuff on the screen. But yeah, other than that, so yeah, what have we got coming up? I know Guy's going to be streaming on Friday, probably about Redis Ohm for Node. So if you're interested in a high-level Redis client for working with the Redis Stack features, specifically search in JSON, Guy will be on the channel talking about that as usual on Friday. Then I don't know, Justin, do you want to say anything about what we've got coming up in sort of other content that we're working on?
Yeah. So we do have a newer version, well, relatively newer version of Redis JSON compared to what we have in our YouTube series. So right now I am working on extending that Redis JSON concepts with newer commands, newer pathing structure, as well as actually integrating Redis search. This is going to pair very well with our upcoming course, RU204. Which is going to be querying and indexing with Redis Search and Redis JSON. And Simon and I are both working on that. So look forward to that coming down the pipeline this quarter. So yeah, those are the two things I'm working on. And then here and there, we're just going to be able to stream as we see fit, maybe doing some live coding. I actually want to jump on some live streaming. I have some pretty far out there ideas that I want to share with everybody and see if I can crowdsource some interesting solutions. I won't reveal too much too soon. I just want to pop out this question real quick from Iman. A non-relevant question. All questions are perfectly fine here. Is it recommended to use Redis with Docker? Absolutely. I think that that's completely valid, especially if you want to give it a try or if you are comfortable with the Docker container environment. I think that that is completely valid. A lot of us actually who work at Redis use Docker containers just because we want to switch between versions for testing purposes, or we just want a smaller Redis footprint. Simon, do you have any opinions on using Redis with Docker versus Homebrew or building from?
Not really, other than it's a great way of trying out different things. So if you want to try Redis with the different capabilities, or if you're working in an environment where you want to try a new version of Redis, so for example, a lot of people might have been using Redis 5 and just not needed to upgrade because it does everything they want. But if you wanted to try like access control lists and the security features that have been added subsequently, or new data types or commands, it's a good way of doing that. And yeah, we provide lots and lots of Docker containers with all sorts of options. We're kind of currently pointing everybody at the Redis Stack container because that gives you all of these capabilities rather than having to pick and choose. I want time series and now I want Bloom. You can have them all in the same database. Somebody was asking about the source code link, so I'm just going to go find that. So I will pop this up. So yeah, Brian, I've not quite finished documenting this yet, but I have documented an older version of it that doesn't have quite all of the data structures. So I will post in the chat a link here, and that's currently a branch link, and that has got the code that I demo with all of those additional data structures, it just doesn't have them covered in the README. But the mechanic for running the example is exactly the same. So yeah, and I will go ahead and finish that README. I don't want to promise, but maybe tomorrow. It's kind of late in the day here today in England.
Cool. And also a quick shout out to L. He zeroed in on the fact that bit fields and bitmaps within Redis can also be used as a unique counter, which is true. There's just a little bit of extra overhead with that, which is totally fine. And it shows that, yeah, you are using bitmaps. So you're one that enjoys the pain of bitmaps. I personally love them. If you've seen we have a Redis explained video on bitmaps. I think they're a lot of fun and extremely powerful. The reason we have our probabilistic data structures is because out of the box they're just up and running. With bitmaps, there's totally different ways of using them for different use cases. So L, what you're doing now is fantastic. And if you want to actually create a probabilistic data structure with bitmaps, I'd love to actually see that, or your unique counting system. I'd love to see that if you want to share that on our Discord channel. Again, the conversation is always continued on our Discord channel. It's discord.gg/Redis Inc. And I'm sorry, just Redis. We're always there, so feel free to ask questions. There's different topic centers, different areas that you can like show off some things, just chat about Redis, or if you have a specific question about any of our university courses or videos or anything like that, we're always there to help.
And that reminded me, I actually made a bloom filter myself using a Raspberry Pi and an 8x8 LED matrix. So I use that as the bit array. I don't have anything that I can like screen share here, but I'll put it in the chat because there's a cool video of it in there, so you can kind of see. Bloom filters can be a very visual data structure, so you can literally see it like checking the thing with flashing LEDs and stuff. That is going in the chat now.
Right on. Yeah, Simon and I both love Raspberry Pi and integrating Redis with Raspberry Pi, as you might have noticed. So if anybody actually enjoys working with the Raspberry Pi, would like to just see if you can cram Redis on it, contact us. We're more than happy to work with you and see what fun things we can create.
Definitely. Okay, I think that wraps it up for today, really. So yeah, as always, we're here quite often on Twitch, and it'll be Guy on Friday up next, and you can catch us on Discord in the meantime. So have a great rest of your day, everybody, and thank you very much for coming.
See you, everybody.
Bye.